Better Buildings for Humans is powered by Advanced Glazings, makers of the Solera line of products. Solera is the leading glass glazing made specifically for architectural daylighting and with extreme insulation performance. Learn more at advancedglazings.com. Hello and welcome to this week's episode of Better Buildings for Humans. I'm your host, Joe Menchefski, and this is the podcast where we take a look at the impact that the built environment has on our health, our wellness, our productivity, and our just general joy of being alive. And of course, we have to talk about sustainable design as well. I have a very interesting show today. I've got a guest that's returning, Dorit Aviv. I also have her partner in research, Eric Teitelbaum. Dorit is with the University of Pennsylvania, specifically the Weitzman School of Design and the Thermal Architecture Lab as well. And Eric is with AIL Research. And we're going to talk about the work that they're doing to help people who end up struggling with the urban heat island effect. Dorit, welcome back. It's lovely to have you.
Thank you. It's wonderful to be back, Joe.
Yeah, it's great. And Eric, it's wonderful to meet you. It's great to have you on the show.
Yeah, nice to meet you, and thanks for having me.
All right, so let's start the way I always like to start, which is allowing our listeners to learn a little bit about our guests. And we'll start with Dorit. I'm going to make you do it again. I'm sorry. Tell us a little bit about your background, why you chose this world of architecture and building science, and then how you came to work with the University of Pennsylvania and the kind of things that you work on today.
Sounds good. So my background is in architecture. I studied architecture. I practiced in design firms. I'm actually a licensed architect as well. But then I turned into research and I did my PhD at Princeton, actually at the same lab that Eric has done his PhD at, also in Princeton, with our common advisor, Forrest Meggers, who is an engineer. And that's when I really started looking at building systems and thinking about sustainable design from the perspective of heat transfer and thermodynamics. So when I started my path at Penn as faculty, I then founded a thermal architecture lab. What we do there is really try to work at the intersection of design, material science, and thermodynamics. We try to bring these fields together because we need all of those to really think about decarbonization of the built environment. When we design buildings, we have to consider how we can design them without relying on fossil fuels. But we also, when we design buildings and we are trying to save energy and thinking about advanced cooling and heating systems, we also have to think about how they affect human health. So my lab collaborates a lot with people in public health and medicine at Penn, as well as with social policy people and with communities that are actually impacted by heat.
Brilliant. All right, Eric, your turn. Tell us about your background and the kind of work you do with AIL.
Sure, sounds great. So my undergrad is actually also chemical engineering.
Oh, cool.
So, started out life as a chemical engineer, and I was drawn to chemical engineering because I love chemistry and I loved building. It turns out as a chemical engineer, you don't necessarily do too much of either of those things. So I took time off. I built tree houses for a while. And when I came back to school to finish my senior year, that's when I met Forrest Meggers, who ultimately became, both of our PhD advisors. And, I was exposed to this world of, sustainability through the built environment. And that's when I started focusing on material science and architecture. So I have a dual degree PhD in those two fields. And most of what I looked at was thermal comfort and trying to maintain comfortable spaces, but using novel material approaches, novel comfort systems, novel thermodynamics approaches to achieve comfort. And I found AIL Research, and the Andy Lowenstein of AIL Research founded this company 37 years ago, I think. And it was perfectly aligned with what I was doing at the time, not only the radiant cooling work, but some stuff with liquid desiccants, which is what they had been working on for several years at that point. But just generally, we focus on thermal technologies, whether it's brine concentration, solar steam generation. Most recently, it's liquid desiccant air conditioning and radiant cooling. So I've got to bring all of these, fields together and focus a lot on energy efficiency and the built environment.
Very cool. All right. So let's dive right into this project you're working on. You guys are working on systems and structures that can help mitigate heat stress. Most of our listeners are acutely aware of what the urban heat island effect is, but just in case. All right, let's take some time, understand the fundamental nature of the problem that this heat buildup in the city creates, what causes it, how serious it is, and how widespread it is now, and how widespread it will become in the future?
Sure, I can start on that. I think it's just important to note that in general, extreme heat is now the deadliest climate-related hazard. It takes a toll of, according to some publications, of hundreds of thousands of lives annually. But it's also a lot of time called the silent killer because it's not as obvious as other environmental health hazards or climate-related hazards like floods, etc. So, this is how we can think about it on the global level, that we have a health hazard that we have to start dealing with in a very different way. Now, urban populations have even a heightened risk, a higher risk to heat exposure. And the reason for that is the heat island effect. So what is the heat island effect? Like its name, it's this phenomenon, but when we look at cities, they are like these hot islands compared to their surroundings. And the reason for that is how we build cities, the materials they're made out of, and the forms they're constructed in. So in terms of materials, we can think about what are urban surfaces. They're mainly made out of concrete and asphalt. Those are heat-absorbing materials. So when the sun heats them up, they trap that heat, they store it, and they emit it back at people. The way we build streets as these canyons, really, that don't let a lot of wind penetrate into them and actually trap solar heat in them, means that there's less cooling available from wind. We actually have this urban canopy layer, is what we call, which is this idea that the city is almost like this mountain where heat cannot penetrate. So there's also anthropogenic contributions, meaning the more we're doing to cool buildings with air conditioning, the more heat we have in our streets. So how does cooling work? It's really heat we take from the inside of the building and dump it to the outside of the building. So in some cities, like Singapore, for instance, the contribution of anthropogenic activities to heat island are very significant. So, all of these things combined create temperature differences that are sometimes up to 10 degrees Celsius, according to some publications. Now, within cities, we also have to realize that cities are not homogeneous. So some neighborhoods are much more heat vulnerable than others. And unfortunately, that also aligns with other type of vulnerabilities. And in the United States, there's a lot of cities where this aligns with a history of marginalization, of redlining, where certain neighborhoods are less invested. And in the end, we're just seeing less greenery there and much lower tree canopy to provide shade.
Okay. Eric, is there anything you wanted to add to that explanation?
Yeah, I guess just from the material science perspective, a lot of these materials, as Dorit said, they're highly absorptive, and it's that re-radiation of the heat that they absorb that is something that is overlooked, not only outside but also inside. And thinking about thermal radiation as it impacts thermal comfort, something we'll talk a lot about on this show, but also I hope people think more broadly about.
Imagine a building where natural light flows freely, solar heat gain is under control, and comfort is unmatched. With Solera translucent glazings, you can create spaces that work better, feel better, and deliver lasting value. Learn how at advancedglazings.com.
Okay, well, let's talk about your efforts to deal with that, the extreme thermal discomfort. And discomfort, from the sounds of it, is maybe an understatement, especially if it's impacting lives. So you set out to create structures to provide some cooling, some thermal relief to people in these highly vulnerable, heat-vulnerable areas, was the language you used. Why can't we just use like air-conditioned shelters or like evaporative cooling systems? You go to Palm Springs, everywhere you sit outside, they've got those little misters going. Why are systems like sort of conventional systems like that not adequate?
Yeah, I guess the main challenge when you're talking about outdoor volumes is that, if you truly want to be outside, you can't condition an outdoor volume. And specifically when you're talking about really hot and really humid locations, things like air conditioning become very energetic. They become very thermodynamically unfavorable. And evaporative cooling, the more humid the ambient condition is, the higher the wet bulb temperature. So that's the combination of the humidity and dry bulb temperature. So the higher the wet bulb temperature, the less effective evaporative cooling is. So, in a dry climate like Arizona, sure, you can get really cold air essentially from evaporative cooling. But in a place like Miami or Singapore, on a really muggy day, you're not going to get much cooling from evaporative systems. And so just in general, we need some kind of solution in order to still provide cooling in environments that have that urban demand. Also on the evaporative side, typically locations where evaporative cooling works, they're drier climates and you are water constrained. So you don't necessarily want to be designing systems that just consume vast amounts of water.
Right. Okay.
Maybe I can just add to that quickly that, that when we look at what, in terms of street cooling, and I think Eric's answer speaks to both indoor and outdoor. When we look at outdoor solutions, there's a kind of a toolkit that a lot of organizations, even the UN, offer to cities to deal with the urban heat island effect. And I would say, those should be layered, right? There shouldn't be just one solution fits all. There actually should be redundancy because some of them work at certain times or certain locations and others don't, just like Eric explained. Trees are your first go-to because they provide shade. So more trees, more tree canopy, even artificial shading is always positive. But I think in relation to heat stress, it's just important to understand that it has a limit, right? Trees can't lower the air temperature, especially in humid climates, much below the ambient air temperature. And sometimes when that's very hot, you need more than shading. And that's where a technology can come in and is meaningful to really deal with those situations.
All right. Well, that's a really good segue to my next question then. Now, if I understand correctly, the structures that you guys are working on, you're employing a new technology. I'm going to read it. It's called membrane-assisted radiant cooling. Okay. Did I get that right? Membrane-assisted radiant cooling. Okay, good.
Perfect.
Can you help us understand how this technology works and why it's revolutionary?
Sure, I'd be very happy to. So to start, I just want to take one step back. If we think about comfort, I think there's this belief, this commonly regarded fact that thermal comfort is psychological. So it's really hard to do research on thermal comfort. But there's a physiological basis, which is more or less heat transfer. So how your body creates heat, how it gets rid of heat to the environment, and the rate at which it loses heat. So if you lose heat too quickly, you get cold. If you lose heat too slowly, that heat builds up and you get too hot. And that physiological basis for heat stress is real. And it's something that Dorit and I have done lots of research on. When you think about a normal building, so you're in an air-conditioned, say, building in the summer, you can go to textbooks and they say that half of the heat that you lose is due to convection. So, the air conditioner, it cools down the air and your skin is in contact with that air. So you can shed heat by convection to the air. But the other half of the heat that your body loses is still via radiant heat transfer. And so what that means is the air conditioner, it also keeps the walls cool around you and the photons that your skin emits. So actually, I don't know if this will work or if this will be clear. Maybe we can try this. Right, this is a handy dandy little thermal camera. Can you see that at all?
Yep, yeah, absolutely.
Yep, so, all of the photons that my body's emitting is what the thermal camera sees. And those photons, they're being radiated out based on the temperature that my body's at. And also all of the surfaces around you are doing the same thing. So if the air conditioner is keeping the surface of the building about the air temperature, then, there's a radiant heat transfer that occurs there because I'm receiving less radiation because the walls are cooler than my body than I'm emitting. So in a normal air-conditioned building, that's about 50-50. Unfortunately, people just kind of say this number 50-50 and don't think too much about it. But what we're really trying to do with these membrane-based radiant cooling technologies is shift that number. So we've talked about how in outdoor spaces, air conditioning is really not an option because you're just you're turning over the air volume so rapidly. But if we can create surfaces that are cold, those surfaces now can absorb the heat that your body is emitting via thermal radiation. And so I can create this cold wall, I can create these cold panels, which is what I make, and they absorb your photons and they heat up the panel ultimately, and you still have to reject that heat somewhere. But it's all about this radiant heat transfer that we're trying to enhance. And so you might think, though, the challenge is going to be if you go to a really hot and humid climate and you have this cold surface out in the wild, it's going to start dripping, it's going to start condensing, right? So that's the innovation with the membrane then. So this concept actually goes all the way back to 1963. Richard Morse in Australia proposed this idea of maintaining a cold surface with an air gap followed by a membrane, and that membrane can allow thermal radiation to go through. But what it achieves is separation of that cold surface from the hot, humid air. So you don't get any condensation from the panel. And, actually, if you look at an air conditioner, for instance, in a really hot, humid climate, about 70% of the work that it's doing is not cooling, it's just drying the air. It's that dehumidification. So that dehumidification is something that, for buildings, is typically useful. You want buildings that are dry. If you have high humidity inside, you get mold growth and just occupant complaints. Outside, we don't want that latent cooling. We don't want that dehumidification if we can avoid it, because, the 100 watts that our bodies need to shed, they matches really well with this radiant heat transfer mechanism that I'm describing. So if you can design these panels that absorb about 100 watts of radiation from your body, then it's a pretty efficient system for if you were not cooling the air. We're just keeping these panels nice and cool, and then they can absorb your thermal radiation through the membrane. That is membrane-assisted radiant cooling.
Okay, so the membrane itself, the material, is some sort of highly or low thermal conductive material, right?
So actually, the key property for the membrane is transmissivity. So if you think of, we talked about the emissivity of concrete and asphalt, right? It has very high emissivities.
Yeah.
This membrane material, if you take a thermal camera and look at the material, you see through it. So that's transmissivity. So as long as it's highly transmissive, then it'll work in that configuration. Unfortunately, there are very few materials that satisfy that requirement. And so, hydrocarbons are a great example. So, polyethylene, polypropylene, that's typically what we use.
Okay. Dorit, you're dying to add something there. What would you like to add?
I was just thinking that the best example I give to explain people how the membrane acts in the infrared range is similar to what glass does in the visible range, right? We can all see through the glass. So that membrane actually allows your body to see through it and emit directly to the panel behind it, which is cold.
Yeah, and an example you can think of too, it's a really kind of strange phenomenon, because typically if you walk into a space that is cold, the walls are cold, and separating, having surfaces around you that are cold, but the air still be very warm, is not an environment that we're accustomed to. One way you can think about it though is, if you go outside and it's sunny, you feel that sun on your skin, right? And you feel warm if it's a warm day. If the sun goes behind the clouds, you no longer feel that incoming radiation. But the air temperature hasn't changed, right? So it's that loss of radiation now that's changing your perception of the environment. In this radiantly cooled space, you are the sun, right? You're the emitter, and you're the source that's responsible for them providing that heating from the panel's perspective.
Okay, so then how are you dissipating the heat that is being absorbed by the membrane or by the radiant cooling?
So with our technologies, there's two versions, which I don't know if I'm jumping ahead here. This is maybe not a good time to talk about them. I don't know. Is this okay? We can talk about the different versions of the technology now?
Yeah, I think that's
Sure,
great.
yeah, let's go.
Okay. So, that's a really good question, though. What happens to that heat ultimately? There's two versions that we make, two patent pending versions of the technology. One is a water-cooled panel. And so it's water, we cool down with the chiller. So it's still coupled to a vapor compression system. And that water ultimately gets heated up by the incoming radiation and gets just recirculated throughout this system. And the chiller will then ultimately reject that heat as it cools the water back down. The innovation on the water-cooled panels, I mentioned that this technology, the concept at least, goes back to the 1960s. Our innovation with the water-coupled panels is that they can be made with plastic heat exchangers that are transparent, more or less, they're a little translucent, let's call it, to visible light. So you can create these beautiful outdoor structures now that, they still connect you with what's on the other side of the panel because you can see through. My kids, they loved looking at each other through the panels.
Right.
But still, this cold surface water is very emissive. So even though the visible light can go through, the thermal radiation is very emissive. And so it's still very good at absorbing your thermal energy. Okay. The other version of the panel, though, which I love, that's a heat pump. So it's this patent pending heat pump, which instead of making cold air, it's like a refrigerator. It makes a cold plane. And so that evaporator now on the heat pump directly absorbs thermal energy. This one cannot be transparent because, it has to be a metal heat exchanger to visible light at least. It cannot be transparent to visible light, but it works exactly the same way. Your thermal energy boils refrigerant that is held in the evaporator, and then it goes to the compressor and ultimately releases energy on the other side of the panel that way. The reason it can be so low powered to the point that you can even start solar powering this kind of system is, again, because for air conditioning, if we're just doing that comparison, cooling the air and drying the air are intensive processes. The amounts of energy that we're actually talking about and the amounts of cooling energy that we're actually talking about are much, much lower, maybe an order of magnitude lower than what an air conditioner would need to provide for a comparable space. So that's why, even though, yes, we're still ultimately coupled to a vapor compression system, the size of these components are much smaller. I wish I had one lying around. The compressor that I usually use is, the size of a can of Coke. They're really small. The electrical load is 100 watts or less per panel.
Oh, very impressive.
Maybe I can follow up on that and just say that's also, so Eric just touched on why this is low energy, and it connects back to your question, Joe, from before of like, why don't you just create air-conditioned cooling shelters? There are municipalities have more and more assigned cooling shelters that are essentially buildings that already exist, where they say, okay, during a heat wave, you can go in there if you don't have access to cooling. But those are places where people have to essentially go to instead of going to work, and they can, lose their livelihood, their income during those days, etc. So they're largely underused, and plus because they're enclosed. For example, during the COVID pandemic, this is a discussion, Joe, that you and I had, like about enclosed spaces that are air conditioned. So a lot of them didn't work during COVID because they were too dangerous from the environmental health perspective. So what we can do here is, with this technology, are open air, solar powered structures. So they're not vulnerable to blackouts that happen a lot of time during extreme heat events. A lot of it is because of the peak demand, right? Everybody needs cooling when you have those extreme heat events, those heat waves. But that's also when a lot of blackouts are happening. So we're talking about this technology, because it's low energy and because it can be open air, can happen on the street without creating enclosures, and is more resilient because it can also be solar powered.
It probably feels a little more comfortable too to just stand in an outdoor, area rather than go into a shelter in a possibly underserved area, right? It probably just feels safer to be there. Let's talk about the conductive cooling as well, because like that sort of conventional conductive cooling is included in this structure as well. Is that correct?
So we've had different variations of how this technology can be applied in both indoor conditions, but also outdoor shelters. One of them was we had, and this is through a PEN initiative for collaboration with communities. We had a collaboration with the community in North Philadelphia. That is one of the most heat vulnerable neighborhoods in Philadelphia, the East Tioga Hunting Park neighborhood. We had a collaboration with North 10, a community organization there that works on environmental health of urban dwellers there in that neighborhood. And what we did was to come up together with the idea of a cooled bus station. Because one thing that community members mentioned was that they lacked any type of bus shelters, right? Not even like shade. But we wanted to provide more than that. And when you think about a bus shelter, that's actually one of the conditions that people in the street are most vulnerable, because they have to stand at one place that's often not shaded to wait for the bus, sometimes for like 10 to 20 minutes, right? And they can't avoid this. They have to be there to get to work or to get to school. So providing bus shelters that are also cooled makes a lot of sense. But when you think about what is a bus station like, there's people that are standing in a shelter, but there's also people that need to sit, or a lot of bus stops have seats in them. And then the question is like, okay, what is the most effective, efficient way of cooling people while they're sitting? And that's when we came up with the idea of cooling the bench as well. In this station prototype we created in North Philadelphia, we called it Tenopy, which kind of combines the name of the community organization North 10 and the fact that it had this canopy. But in the Tenopy, the radiant cooling system and the conductive cooling system work really nicely together, because when you're standing in the bus stop, you're radiantly cooled by panels that are surrounding you. When you're sitting, you're conductively being cooled by the bench you're sitting on. And the pipes that run the refrigerant from in the bench are actually using refrigerant that it's already been slightly heated by the cooling panel. So we don't need to spend more energy on that. And it can be at a higher temperature so that the surfaces don't condense. But because you're sitting on them, you're getting this additional efficiency of cooling.
Brilliant. I love that. Let's talk about the physical appearance of the structures. And my next question was supposed to be about the different iterations, and then I forced poor Eric to have to do it to cover that earlier. But let's talk about then what it physically looks like. What do people see when they're walking down the street? How do they identify the structure, and what are the various bits and pieces doing? We know individually what you're trying to achieve, but let's talk about how the whole thing fits together and what people see.
I mean, in the case of the canopy, it was really like, and we designed it in wood. It can be done in different materials. We really tried to make it something that we could build ourselves and deploy and build together with community members. You really just see a bus stop that has panels. We actually use the surface of the panels to give people information about radiant cooling because most people are not familiar with that. So when you're actually looking at the bus station, the TANO prototype we designed, it's not very different in what it looks like from just a configuration of a bus stop that's sheltered and has a standing position or a space for standing, a space for sitting. What we did is with the radiant panels cover the whole area, they really cover the walls of the area where people could stand. But we actually put on the panels themselves information about how this system works so that people understand. They can actually stand there and read about the system and understand it. And then when you're sitting, we also added, in the sitting position, we added information about the dangers of heat stroke and how you can avoid it. So, and the whole thing was done in collaboration with the community. So then community members tested it. They gave us feedback. They filled out surveys about their thermal sensation in the space. But what we did next, and maybe we can get into what does this look like? It has many different iterations of what it looks like. We then worked on a structure that was really just about the radiant cooling and used Eric's and AIL research, the translucent panels they've developed. And we worked with an architecture firm, Henning Larsen, that is based in both Denmark and New York, on building a heat shelter that's open to public in New York. And that looked very different because there we tried to create a very expandable modular system. So we had a 4-foot by 4-foot module that had panels on, you could make different combinations of them, but essentially it has a canvas shaded roof, the panels underneath. This was water-based, the way that, the chilled liquid in the panels was water, and you could make many different combinations or keep expanding it. The whole idea is that the more cooling you have, the more solar panels you need on the roof to power them, but there's a nice correlation between the amount of power that a solar panel would provide on a roof of such a 4-by-foot module to the amount of cooling you need to cool people underneath it.
Yeah, and I can talk about also, there was another project called the Cold Tube. This was a structure that I worked on during my PhD. I was in Singapore, and to my knowledge, that's the first actually, built membrane-assisted radiant cooling pavilion. So, I mentioned that we found this paper from 1963 that talked about the idea. I don't think anyone had built it in the wild yet. And so in Singapore, we constructed this pavilion called the Cold Tube. Adam Rieseneck at University of British Columbia and Forrest Meggers were heavily involved in this project as well. And the idea was, again, if we can make this technology work in Singapore in a notoriously hot and humid environment, it'll work anywhere. So this was a demonstration kind of project. It was still very early stages of the technology. So if you look at pictures of this, we're still using these capillary mat heat exchangers. Everything was fabricated just out of wood on site. The structure itself, one term that we haven't talked about that's really important for radiant heat transfer is view factor. So you basically want to make sure your body is seeing as many of these surfaces around it as possible to maximize the effect. So we had this, the Cold Tube. It was this long hallway essentially of membrane-based cooling panels. They were not transparent, so it was a little dark and not claustrophobic, but your connection to the outdoors wasn't necessarily there as much as it is now with current designs. But, the structure made it very clear, at least, though, that this is a technology worth pursuing and can really have a big impact on outdoor thermal comfort and relieving heat stress.
Right on. Tell me about the test protocol. Dorit, you sort of alluded to it a little bit, but let's talk a little more. How did you confirm, we know how different people perceive heat, or we know that there's significant variation. So how do you account for that in your testing?
I can talk about the measurement tools a little bit that we use.
Sure.
One of the challenges with talking about radiant cooling and thermal comfort is, if you think about what everyone's used to changing, it's the thermostat. If you get too hot, you turn your thermostat a little bit cooler, and it tells your air conditioner to reduce the air temperature in the space. There's nothing really that we have available on the market, at least, to do that on the radiant side. But what we're really looking at when we assess whether a radiantly cooled space is working, it's the mean radiant temperature. So just like the air temperature is an indicator of, the convective heat transfer that your body will experience in a space, the mean radiant temperature is an indicator of the radiant heat transfer that it'll experience in a space. And so there's another spin-off company from Forrest Megger's lab called Chaos Sense. They make these little cubes, and oh my goodness, actually I have a really old one. But it's this thing that we put in a space, and each of these little nodes is a non-contacting thermal sensor, just like you go to the doctor and they roll that thing over your forehead and it tells you your temperature.
Yep.
It's that, and it's looking at a 90-degree field of view, and it reports the average temperature in that field of view. And there's a bunch of them, so it tells you the average radiant temperature around you. And so now we know if we're standing within a couple feet of one of these panels, what their mean radiant temperature is and how much radiant heat transfer your body can experience.
Okay.
And all of that, evaluation adds up to, I think, your question, how do you evaluate heat stress relief? Basically, we take the accumulation of factors that we have there to understand what the body is experiencing. So in our recent paper, that was where we really measured these factors in the canopy structure, we look at the combination of the air temperature, humidity, mean radiant temperature. All of these things together can tell us how much heat stress the body is experiencing in terms of watts. And maybe Eric can explain a little bit more about that. But I also want to add that in addition to these environmental factors that we measured, we also did surveys, and that's true for the work on the cold tube and on the canopy, where we asked people that stayed for a while in these shelters to fill out surveys about their thermal sensation. And there is a protocol for that. You're basically rating, are you slightly hot, very hot, neutral, or slightly cold, etc. And our conclusions from all the surveys we did at the canopy, for instance, was that people had a very positive reaction to both the radiant cooling system and to the conductive cooling. They reported, in general, a really high percentage of thermal satisfaction. I think there's also a simulations technique that we have developed to predict how much a cooling system, or an architectural manifestation of that cooling system, right? Those thermal shelters, how much are they really achieving in terms of lowering mean radiant temperature, therefore lowering your heat stress. So in order to predict that, it's a very different thing than just saying, well, you'll go down to 26 degrees or Celsius, or, etc., which is kind of the threshold that a lot of people talk about for air conditioning. But how do you do that? So we have come up with new ways to simulate the heat in the urban environment and understand the impact on your body.
So both in terms of, the actual quantitative measurements that you took, and in terms of the qualitative feedback that you got from users, was there anything that came out of it that says we have to make a couple of changes? Were there learnings that you're incorporating into the design?
Yes, I think one thing is that, Eric and a team in Singapore did much more just number of surveys in the cold tube than we were able to do with the canopy structure. So we would like to just do a longer and, surveying period with more participants. And for both, also for the clima cover structure, which was open to public, but we would like to get more data out of it and are hoping to rebuild it this summer again and have it again open to public. But there's also something we learned which was interesting, which was the bench we designed. People had very positive reactions to it, but when we measured the actual heat flux from the surface directly to your body, it wasn't performing super well. It wasn't super efficient because of the materials we used. So we're currently fabricating another version of it, where instead of, we had a bamboo surface, which is higher conductivity than just regular wood, but was still limiting the conductivity of the surface. Now we're using a low carbon concrete, and we're going to test that with people. So yeah, there are a lot of improvements we can make to the system, but having it out there and being able to just build it quickly and build it together with the community for the bus stop prototype was really our goal.
Yeah, I think just one of the challenges in general with implementing this type of system is that just by the nature of radiant heat transfer, it's not just about what the system provides, but you have to think a little bit more about the environment that it's in as well. So what I mean by that is if there's a wall that's in direct sunlight, say, adjacent to the system, you not only need to add shading to that from that wall or in a position so your body doesn't see that hot wall or hot road surface that you're next to. Otherwise, you drown out the signal that you're getting from the cold panels.
Solar heat gain doesn't have to be a design challenge. Solera translucent glazing units help architects create buildings that not only work better, but feel better, balancing light, comfort, and energy efficiency. Discover how to design higher value spaces without compromise at advancedglazings.com.
Okay. Well, let's talk business for a minute. How are we commercializing this? How are you guys taking this to the market?
So we have plans to spin off a company. The working name right now is Clearly Cool, and this is using the AIO research technology. And we're looking for different applications. So on this podcast, we've talked a lot about the need that exists for human shelters. We actually have some funded research right now on animal cooling as well. So in animal husbandry applications, heat stress is just as big of an issue. So whether it's keeping dairy cows cool, whether it's keeping pigs cool, that's something that we're actively looking at on the business side. But yeah, we're hoping to either manufacture these at small volumes and sell them or license the technology to others.
Right on.
And we have at Penn, at the Wharton School of Business now, a bunch of graduate students looking into commercialization opportunities or market opportunities for that, both in the private sector and in the public sector. We also have collaborations, just like I mentioned with Henning Larsen. There are other architecture firms that are really interested in applying this solution in the real world. And also more and more, I'm receiving requests from community organizations, as well as different type of design firms, even landscape architects, to collaborate with them and think about how to apply this solution.
Yeah, I think everyone is acutely aware of the need for cooling technology that is low power and efficient. I think a big challenge and a reason I love collaborating with Dorit is the ability to demonstrate this technology. It's so different from air conditioning, and everyone is just so accustomed that if you want cooling, then you go out and buy an air conditioner. It doesn't have to be that way, but making that change, that's a pretty big ask. And so these demonstrations are really important to show what can be done on the radiant side.
How do you make it affordable for, the big sort of tropical cities that may not have the same economic resources as, say, New York?
So at scale, these things, should be fairly cheap. That's certainly something that we struggle with a lot. Economy of scale in the HVAC world is, it's hugely important. You go to Home Depot and you buy a $300 window air conditioner. We're providing much less cooling ultimately than that window air conditioner does because we don't need that much cooling if you have these radiant systems. But until you get to those huge volumes, it's really hard to drive the costs down. But with time, there's no reason why we can't get there.
Right on. Okay. Let's see. Is there a way to adapt the learnings and, this new technology that's now commercialized? Can you adapt that to other cooling challenges?
Sure. So, certainly on the agricultural side, as I mentioned, that's one thing that we're looking at now. I think there are so many other applications as well, whether it's these cooling shelters, whether it's even just outdoor dining, right? You go to an outdoor dining place and they have these propane heaters. For one, these radiant cooling panels can also provide radiant heat. So it would be the same system that can provide both, but now we can offer relief in the summer. Athletics, maybe. You think about baseball players sitting on a dugout, just put some cooling panels over them, and now there's some active cooling, keeping people happier on the bench. There's a million different ways that I think these things can be applied. Maybe all of them look a little bit different in terms of maybe transparent nature is not important for some of them. Maybe it's really important in certain applications. But yeah, there's a million ways you can apply these in the field, I think.
And I think one thing that we should mention is that we've really focused in this conversation on outdoor cooling because we've seen how important this solution is for the outdoor, just because there's a lot you can't do in the outdoor where, you can't air condition like entire volumes of streets, right? That's not possible. And you had a conversation before, there's limits to other solutions, and this really provides a solution that can be applied almost in any region of the world. But we just want to say also this is not limited to the outdoor, meaning there are radiant systems already installed in many buildings, radiant cooling systems. And again, the challenge has been that you needed to couple it with dehumidification system in humid climates, which then takes away a lot of the efficiency. But if you have this membrane, there's also this possibility where you can open the windows and not control the air temperature at all inside the building, but provide cooling through the radiant panels. So there's also, we believe a very good incentive to apply this indoors for energy efficiency.
Besides the brilliant technology, you know what I really like about this? I just listened to both of your answers. There are some really cool high margin market segments that want this product that could supplement, I'll say the more humanitarian needs, right? Which is always a challenge when you're trying to create something for an economically challenged group of people. It's always about money. But if you've got these other applications where the restaurants, for example, a high-end restaurant, oh my gosh, now you've got cash flow that'll help to make it, more affordable for, like I say, the more humanitarian applications. So absolutely love the way this is working out. Okay, we're getting close to the end of the show. I've got to ask my $1 million question. I just have to. So there's a question I ask in every episode. Dorit has answered it before, but I'm going to make her do it again. So that question is for everybody, and it's meant to be answered from whatever perspective you'd like. Okay? So here goes. We'll go with Dorit first, just because she's got experience. What makes a great building?
I actually love answering this question. I don't mind answering it twice because buildings are such complex systems and they touch on so many aspects of our lives and the ecology around us that there's many ways to answer this question, and all of them are not exclusive of one another. So I think last time, one of the things I mentioned was the social aspect and how if a building is able to transform the neighborhood that it's implemented in and connect people to their neighborhood and create safe outdoor space for them to gather in, that's an example of a great contribution to humankind that a building can do. But today I'm going to actually talk about another aspect, which is the sensory one. And the reason I'm thinking about it a lot these days is because I just took my students to visit San Francisco and Berkeley last week. And we had a lecture by Gail Brager, and she focused on her recent book that she co-wrote, which is about experiential architecture. And what they talk about is architecture that can stimulate multiple senses at once. So because buildings are all-encompassing, they affect our sense of touch, smell, light all at the same time. And the idea is that the more you can stimulate our senses, the greater your experience is of the building, of the architecture, and it leaves a long-lasting impression on you, but it also ignites your own curiosity and your own pleasure. This connects to this concept of that I'm not sure if we talked about before, maybe in the context of these cooling structures, but we do think about this concept of thermal anesthesia, which is we can move beyond this idea of just neutrality, that buildings need to be just thermal shelters that create neutral environments where we're just comfortable, neither hot nor cold, and move beyond that towards the idea of thermal pleasure. Can actually a variety of experiences, a contrast, just instigate pleasure through activating your senses. And if you can do that in more than one way, more than one sense, then your experience is even heightened. And Mark Decay and Gail Brager's new book, Experiential Design Schemas, it gives many different examples of buildings that do that.
Very cool. You'll have to introduce me to Gail. Was that her? Yeah, you'll have to introduce me for sure, because I definitely want to talk a little bit more about that. Did you ever read Lisa Heschong's book, Thermal Delight in Architecture?
Yes. Yeah, this is one of the required readings in my environmental systems course to graduate students in architecture.
Very cool. All right, Eric, what's your answer? What makes a great building?
So I'm an engineer, so I'm going to take the nerdy approach here. But I think there's a huge opportunity for designers to embrace refrigeration. And what I mean by that is there's so many decisions that get baked into a building from the design phase that really impact the thermodynamic performance of refrigeration systems that we don't necessarily think about, but we should. So I've taught classes in the past where design students are physically building heat pumps. So, brazing things together, thinking about ways that not only do you want to cool or heat the air, but you can cool or heat maybe a surface, or you can cool or heat a bench. And once you start doing that, you can think about how design can be used as a tool to minimize lift and therefore increase performance. And that's something that, I think is really fun to teach, but can be really, really meaningful in terms of design implications. And so it makes things like radiant cooling become a little bit more self-evident, I think, if you're really thinking strategically about the best way to engage people thermally with surfaces around them. Designers are in charge of what the space looks like and where you have walls, where you have thermally activated surfaces maybe. And there's just such a huge opportunity there to really make all electric buildings of the future be as efficient as possible.
Wonderful. Now, before we go, Eric, I'd like to pass on compliments to the artists. The artwork that's behind you is absolutely wonderful. And please make sure that the artist receives that compliment. Thank you very much for your time. It's been an absolute joy talking to both of you. I know we went long, but it was worth every minute of going long because this is some pretty important stuff that the world needs to know about. Thank you for your time.
Wonderful.
Thank you
Thanks,
so
Joe.
much for having us and the opportunity to share this. Thank you, Joe.
It's a pleasure. We'll be talking. Take care.
Thanks.
We hope you enjoyed this episode of Better Buildings for Humans. For more information on the world's best light diffusing and highly insulating glass glazing, please visit advancedglazings.com.